Okay, the problem that we're looking at from chapter 2 talks about Sturgis guideline. Sturgis guideline is a formula used to determine the ideal number of classes in a frequency distribution. If you remember when we were first constructing frequency distributions, the general rule in your book said something to the effect between 5 and 20 classes, depending really on the sample size. For a small sample size, you'd want a smaller number of classes. For a large sample size, in the tens of thousands, you would use a number that's significantly more. Okay, so Sturgis guideline is a way of imposing some rigor on that general rule of thumb. And Sturgis said that the ideal number of classes in a frequency distribution is 1 plus the log of n divided by the log of 2. Now, at this point in the course, people were like, oh, what's a log? And if you need to learn that, what you should do is go over to the math lab and ask to borrow an intermediate algebra book and ask a tutor to go through basic log operations with you. And that usually comes in around the last third of an intermediate algebra book. So the idea here is that we are going to give you the number of data values. In other words, if n, our sample size, is between 16 and 22, the ideal number of classes is 5. If it's between 23 to 45 inclusive, the ideal number of classes is 6. So again, I'm saying that n represents the number of data values. And we could test this out. We could take a number in the middle here, and with our calculator, say if we want to just randomly choose 20, I can say log of 20, that's my log of n up here, log of 20 divided by log of 2. Okay, so I've got log of 20 divided by log of 2, and then adding 1. And you can see on the display that 5.32 classes, in other words, 5 classes. And so the twist in this problem is that although they give you the formula that works when you're given values of n and asked to produce the ideal number of classes, they don't give you the formula for going in the other direction, and that's the idea behind the problem, is that you're supposed to be able to fill in these blanks here with your boundaries. So if we think about it, our lower bound here is going to be 46, and what we really need to be able to compute is our upper bound. When we have 7 classes, what's the highest number of data values that we should use 7 classes for? So to do that, I'm going to let my ideal number of classes equal a second variable x, and so ideal number of classes, x equals 1 plus log of n over log of 2. I'm going to use my properties of logarithms to solve in terms of n, because that's what I'm missing from my table down here. So basic algebra, x minus 1 equals log of n over log of 2. I'm going to multiply both sides by the log of 2, which clears that from the right side of the equation, right? If I multiply this by log of 2, I get rid of it, which is the point. Now I've isolated my variable on one side of the equation. The next thing that I'm going to do is use my properties of logarithms to treat this as a power. So I have log of 2 raised to the x minus 1 power equals log of n, and then what I do is I take the log of both sides. So my final formula is 2x minus 1 equals n, and that's really what I need. So let me rewrite that over here. New formula, n equals 2 raised to the x minus 1 power. And so that's what I'm going to use to solve for these blank spaces down through here. So I know that x is 7, and so one thing that I suppose I could do is say 2 to the 7 minus 1, which is 2 to the 6, and 2 to the 6 is 64. And it makes sense superficially to do this, but that actually doesn't produce our final answer. If you use 7, then what you're going to get is the midpoint of this distribution and not your upper bound. So the upper bound, the way I think about it, is the boundary between 7 and 8 is 7.5. And so if I use 7.5 instead of 7, what I have is kind of the cut point. So 2 times 7.5 minus 1 equals 2 raised to the 6.5 power. And so I'm saying 2 raised to the 6.5 power. And I end up with 90.5. I could either round that to 90 or 91. Doesn't really matter in this case. Okay, so then my next boundary is going to be 92. And I'm going to apply the same principle. Use 8.5 as a boundary, so I'm saying 2, 8.5 minus 1. And so 2 raised to the 8.5 minus 1. Let's try that again. 2 raised to the 7.5 power is 181-ish. And so my next bound is 182. Upper limit here, again, I'm going to use 9.5. Okay, remember this was a minus 1 in the exponent. 2 to the 9.5 minus 1 is 2 to the 8.5. So 2 raised to the 8.5 power is 362-ish. Okay, so I hope that helps. And from here you can just repeat the same pattern to fill in the rest of the blanks. And again, this is really a favorite test problem of mine. It shows up as 2 distinct test questions. One is using this formula, where x equals 1 plus log over n divided by log over 2. And then the second test question usually is something using that formula. So go back and review the information in your book. You may want to look at this video again, and certainly feel free to ask me about this in our face-to-face class. And I hope that this little explanation helps. And again, problem 32 on page 55.